Thevenin's theorem. So the statement says any given linear two-terminal network can be equivalently represented by a series combination of Thevenin voltage and Thevenin resistance, which is measured looking back across the same two terminals, making all the independent sources inoperative. So we have seen previously also when we looked into the superposition theorem, when we make the sources inoperative, especially the independent sources, if it is a voltage source, we will make it as a short circuit, and if it is a current source, we will make it as a open circuit. So any circuit that is given to you, any complex circuit that is given to you, as per the Thevenin's theorem, we will reduce the circuit and represent it as a series combination of Thevenin voltage and Thevenin resistance. So let me explain this further with an example. So if you look here, I have a circuit where I have considered the applied voltage is E, and I have these resistances R1, R2 and R3. The load is represented as RL, and the current that flows across the load is represented as IL. So as per the Thevenin's theorem statement, this says that this circuit can be reduced to an equivalent circuit wherein I can represent this as a series combination of Thevenin voltage and Thevenin resistance. Now how to do this is, first you need to identify in the circuit where the load is connected. So identify the two terminals across which the load is connected. So in this circuit, these are the two terminals where the load is connected. So what we need to do is, once you identify the load, the two terminals across the load, you have to open circuit it. Okay, you have to remove this load and make it as a open circuit. So what remains is only this much part of the circuit. You have the applied voltage E, you have the resistance R1 and resistance R2 and resistance R3. So that is what I am representing here in the form of a box, the dotted lines. So it is only this much part of the circuit that remains. Okay, so this circuit, the one which is marked within the box, can be equivalently represented as a series combination of Thevenin voltage and Thevenin resistance. So once you find out what is the Thevenin voltage and Thevenin resistance, all we are going to do is, whatever we had removed, the load between the two terminals, we are going to connect that load and then mark what was it, whatever the value of IL was represented here. So mark the load current IL. Now say you want to compute the value of the load current IL, all we need to do is apply KVL to the circuit. So you have IL is equal to V Thevenin divided by R Thevenin plus RL. So any complex circuit that is given to you, first identify where the load is connected, identify the two terminals, remove the load, and the circuit will be an open circuit. And then you have to reduce the remaining part of the circuit as a series combination of Thevenin voltage and Thevenin resistance. After that, replace the load and you can compute how much is the load current. So now under Thevenin's theorem, we have different cases because the circuit can have independent sources, it can have dependent sources. So depending on the type of sources that are present in the circuit, we have three ways in which we will be calculating. Another thing to be noted here is this Thevenin voltage that we are computing, right? This Thevenin voltage is also called as the open circuit voltage. So we can call this as VOC. Thevenin voltage is also called as open circuit voltage because we are computing this voltage by considering all the sources being present. We are computing this with all the sources being present, and this voltage is computed. Say for example, this is the circuit I have, right? So in this circuit, how to compute Thevenin voltage is that I will be considering this as it is. So you have this open circuit terminal, right? So here you will be computing the Thevenin voltage across this open circuit terminals. Similarly, say you want to compute R Thevenin. To compute R Thevenin for the circuit that is shown here, what we are doing is we are making all the independent sources inoperative. So when we make the independent sources inoperative, if it is a voltage source, it will be considered as a short, right? So I can write this as a short. I have resistance R1, I have resistance R2, resistance R3. These are my open circuit terminals, and this is the resistance R Thevenin computed when looking back into the circuit. So if you observe here, what do you see? You have R1 parallel with R2. The resultant is in series with R3. So this will be the value of R Thevenin. Whereas V Thevenin, if you want to compute, it will be the voltage that is developed across this resistance R2. Okay, which in this case can be computed using the voltage divider rule. So first task would be, whenever a circuit is given, identify where the load is connected, remove that load, you will get an open circuit terminals, right? Across those open circuit terminals, first measure V Thevenin. After that, make all the independent sources inoperative, compute R Thevenin obtained when looking back into the circuit. Once both the V Thevenin and R Thevenin are computed, draw them as a series combination of Thevenin voltage and Thevenin resistance. Whatever you had removed, the load, connect it back and compute the load current. Depending on the type of sources that are there, what are the various cases that we have. Case 1, we have circuit which contains passive elements. When I say passive elements, it could be resistor, capacitor or inductor, and then you have only independent sources that are present. So the example that I demonstrated to you just now, this is a case where you had only the independent sources, right? Only independent sources are present. So what we will do is, first we will identify the terminal where the load is connected. Okay, determine the open circuit voltage. Open circuit voltage, I told you, is nothing but corresponding to V Thevenin. So you will compute V Thevenin and then you will compute R Thevenin, making the sources inoperative, similar to what I demonstrated here. You have made the voltage source inoperative, because voltage source, if it is inoperative, it has to be made as a, explain this with a numerical. So here's an example which says you need to find the Thevenin equivalent circuit for this particular circuit shown. So first thing, look at this question. It has only independent sources. 32 volt is an independent source, 2 amps is an independent source. Now to compute the Thevenin voltage, you need to identify the two terminals where the load is connected. So this is where RL is connected. I have identified the two terminals. Now I'm going to remove this load. Okay, so let me see what is the equivalent circuit that I get. Now across these two terminals, I need to compute the Thevenin voltage. So I'm going to mark this as V Thevenin. So since there is no current flowing across this 1 ohm resistance, I can simply neglect this, right? So I can further redraw this particular circuit as 32 volt. Now when you look at this Thevenin voltage is the voltage developed across this point and this point, right? Because we generally consider this as ground. So in a parallel circuit, we know that the voltage developed across this parallel branches will be the same. So V Thevenin is the voltage developed at this point, or I can say it is the voltage developed across 12 ohms resistance. Now in this case, you cannot apply the voltage divider rule if you want to compute V Thevenin. The reason, because you have a current source here. If there was no current source, directly I could have computed Thevenin voltage using the voltage divider rule, correct? So the only way that I can compute the voltage across this 12 ohms resistance is by applying KVL to this particular circuit. So use the concept of mesh analysis. Let me consider this as mesh 1 and this as mesh 2. I will name this as current I1 and this current as I2. So if you see here, the current I2 is opposite in direction with the 2 amps, right? So I can write this current I2 to be equal to minus 2 amps. Whereas when I apply KVL to the first mesh, I have this as 32 minus 4 times I1 minus 12 times I1 minus I2 is equal to 0. So I can compute the value, obtain the value of I1 to be equal to 0. Now I said Thevenin voltage is the voltage developed across 12 ohms resistance, right? So across this 12 ohms resistance, you see this is positive, this is negative. So I need to consider I1 to be the dominant mesh, because here the Thevenin voltage here it is plus, right? So I can compute Thevenin to be equal to I1 minus I2 into the value of resistance, that is 12. So here I get this as 30. Now to compute the value of Thevenin, we need to make the independent sources inoperative. So in our case, we have to consider this original circuit, right? The reason being, we excluded this resistance because there was no current that was flowing in this circuit. So now when you want to compute Thevenin, consider this particular circuit. Now make this voltage source inoperative. So voltage source will be considered as a short. The current source will be considered as a open circuit. So you get the circuit as, and Thevenin is computed as a resistance obtained when looking back into the open terminals. So this is Thevenin. Now what do you see? You have 4 ohms resistance in parallel with 12 ohms resistance, and this resultant is in series with 1 ohms resistance. So Thevenin will be equal to 4 parallel with 12 plus 1, 4 ohms. Finally, the question says to find the equivalent circuit, right? So for equivalent circuit, you have to now draw the circuit as a series combination of Thevenin voltage and Thevenin resist. So this is what you get. But in this particular circuit, we had a load. So try to compute how much is the value of this load current. So we have reduced this entire circuit, this open circuit part, into a Thevenin voltage with a resistance in series. This Thevenin voltage is 30 volt that we obtain, and Thevenin is 4 ohms. Now connect the load whichever we had removed. So RL is equal to 6 ohms. Find out how much is the load current. So IL will be equal to what? You have the voltage, source voltage, that is Thevenin, divided by the sum of the two resistances, Thevenin plus RL. So you get this as 30 divided by 4 plus, which is equal to 3 amp. The circuit contains passive elements, dependent sources and independent sources. So whenever you have both dependent and independent sources, you cannot solve it in a regular manner. So that is why first you need to determine the VOC. VOC is nothing but equal to the Thevenin voltage itself, okay, when all the sources are present. So the procedure to compute the Thevenin voltage will be similar to what we have seen previously. Name that is interchangeably used. Then in this case, since you have dependent sources, you need to find ISC. ISC corresponds to the short circuit across the terminal AB. So these AB here in this case corresponds to the open circuit terminals which initially you used to compute the Thevenin voltage. So now what you need to do is you need to make it as a short to compute the value of the short circuit current. Then to compute the value of Thevenin, you will be considering it as a ratio of the Thevenin voltage divided by the short circuit current. So in the case where you have passive elements, dependent sources and independent sources, compute the Thevenin voltage first. After that, determine ISC value, that is the short circuit current value, and then compute R Thevenin as a ratio of Thevenin voltage to the short circuit current. Let us solve this and better understand with an example. This is a second example which says you need to find the Thevenin equivalent circuit. So in this question, clearly you can see you have an independent source which is a 4 volt, and you have a dependent current source which is equal to Vx divided by 4000. Step is in similar manner. You need to compute the Thevenin voltage. Moreover, here the network is already open circuited for you, right? Vx they have specified. So Vx, since they have specified, this is nothing but directly you can consider this as your Thevenin voltage, which we also call it as the open circuit voltage. So let us see how to compute this value. So first step would be to find V Thevenin. Now if you see here, since this circuit is already open circuited, there isn't any current. So it can be considered as a negligible value. So when I'm drawing here in this case, I will simply ignore that resistance and write this as plus minus V Thevenin. Okay. Has everybody understood here till now? Has everybody understood till here? Why I ignored the 3 kilo ohms resistance is understood? Because there is no current flowing. So I can simply ignore that and draw this way. Now, generally we could say that this Thevenin voltage V Thevenin is the voltage developed across this particular dependent current source, right? In this case, since this is a dependent current source, it becomes very difficult for us to compute the value. What we will do is, instead of applying KVL to the circuit, we will apply KCL at this particular node. Now since I have represented this open circuit voltage as V Thevenin, this voltage also can be represented as V Thevenin. So Vx, because I have written here, right, Vx is equal to V Thevenin is equal to Voc. So I can call this as V Thevenin voltage. I will name this particular node, I will name it as node A. Since this is a dependent current source, I cannot apply KVL, so I am applying KCL to the node A. So on applying KCL at node A, you have to consider what? Whenever you are applying KCL at a particular node, we will be considering the current leaving the node unless and until you have some source being connected. So across this particular branch, I will assume the current is leaving, whereas here directly I can see the current is entering the node. So I can write this equation as VA minus 4 divided by 2 kilo, this is the current that is leaving, equal to the current that is entering the node. Only one current is entering the node, and this is equal to V Thevenin divided by 4000, right? So this node voltage will be same as this particular node voltage. So this VA is nothing but equal to V Thevenin. So I can rewrite this particular equation as V Thevenin minus 4 divided by 2000 to be equal to V Thevenin divided by 4000. What do I get? The value of V Thevenin as? So V Thevenin is equal to 8 volt. So to compute ISC, what did it say? It said to find the short circuit current, you are supposed to make the terminals as a short circuit, right? So I will redraw this circuit once again, okay? But now you have to make sure that you include the 3 kilo ohms resist, and this open circuit terminal now has to be considered as a short and marked as ISC, that is the short circuit current. Now initially this terminal was what? This terminal was represented as Vx, right? When I make this terminal Vx as a short, it is equivalent to saying I am making Vx is equal to 0 volt. So when I make Vx is equal to 0 volt, what happens to this dependent current source? 0 divided by 4000 is equal to 0. So I can redraw this particular circuit simply as ISC will be equal to, just apply KVL to this circuit. ISC will be the source voltage divided by 2K plus 3K, 0.8 milliamps. R Thevenin will be equal to, R Thevenin is equal to V Thevenin divided by ISC. So this is 8 divided by 0.8 milli. The value is 10. So question says you have to find the Thevenin equivalent circuit. So let us draw the Thevenin equivalent circuit. When you draw the Thevenin equivalent circuit, this is going to be a series combination of V Thevenin and R Thevenin. Since this was already open circuited, right, we didn't have any load resistance, so this is what you will get. You have to keep it as open circuit itself, but specify the value. V Thevenin was 8 volt, R Thevenin is 10 kilo ohms. Case circuit contains passive elements, that is a resistor, capacitor or inductor, and it consists of only dependent sources. You do not have any independent sources. Okay, only dependent sources are present. So when you have only dependent sources, there is no energy source in the circuit. So that is why the Thevenin voltage will be equal to 0 volt directly. After that, to compute R Thevenin, what we need to do first is, you need to connect 1 amps current source to the terminals AB, which are open circuited, and determine VAB. And then R Thevenin will be equal to VAB divided by 1 amps. So this is the procedure. So let us look into that, how to solve this particular problem. So when you look at this particular problem, you can clearly see there is no independent source, right? So when there is no independent source, no energy source, so basically your Thevenin voltage, which is also called as the open circuit voltage, is equal to 0. Now you need to determine VAB. Okay, you need to determine. So to determine VAB, since you don't have any energy source, you need to connect 1 amps current source to the terminals AB. So this circuit we will connect 1 amps across the terminals AB. So 1 amps current source is connected to the open circuit terminals V, A and B. You need to compute the value, right, of this VAB, because here Vx is nothing but corresponding to VAB. So since there is a current source here, which is a dependent current source, and there is also a current source here, let me consider this as node, say B. Let me apply KCL at node B. Since there are current sources being connected, you can't find out what is the voltage developed across this, right? VAB is what we want to determine, which is the voltage developed across this 4 ohms resist. So on applying KCL at node B, you see this current source is leaving, this branch I will consider as leaving, whereas this branch the current is entering. So I have this as half times Vx plus the voltage developed across this resistance is nothing but VB, right, divided by 4 is equal to 1. The voltage VB is nothing but equivalent to VAB, or it is equivalent to Vx. So I can write this as half times, let me represent all of them in terms of VAB. So this is VAB plus VAB divided by 4 is equal to 1. So find out how much is the value of VAB. So VAB is equal to 1.33 volt. Next we need to find R Thevenin. So to find R Thevenin, the procedure says it is the ratio of VAB divided by the current source that we connected, that is 1 amps. So you have R Thevenin to be equal to VAB divided by 1 amps, which is equal to 1.33 ohms. Next, you need to draw the equivalent Thevenin circuit. So when you draw Thevenin equivalent circuit, in this case V Thevenin is 0. Generally we represent this as what? A series combination of Thevenin voltage and Thevenin resistance, right? So in this Thevenin voltage is 0, so you are left with only the resistance, that is R Thevenin equal to 1.33 ohms.